Today is Friday, June the 14th at 1:09 p.m. and we're at the Micropropulsion and Nanotechnology Lab at George Washington University in the Department of Mechanical and Aerospace Engineering, basement of Tompkins Hall. This is a alpha test experiment for the Micro-Cathode Arc Thruster PhoneSat experiment, and this is a project jointly between George Washington University and NASA Ames Research Center. And what we have here is a test bed setup completely made out of prototype parts and components and subsystems of a microcontroller based control unit, which will trigger two physical thruster channels and one logical channel to be displayed on an oscilloscope. And the system will be demonstrated in such a manner to show independent operation of the three channels and simultaneous operation of the three channels at the same time. And we may get a chance to see inside the vacuum chamber so that the arc discharge within the vacuum chamber can be shown, and the arc discharge outside of the vacuum chamber can be shown. But at this point, I'm just going to pan around, and I'm going to show you the vacuum chamber where there is already a thruster inside, and that is a prototype thruster made out of certain materials that are outlined in the experimental notes. And the vacuum chamber has been already pumped out. There is a oscilloscope which is actually slaved to the chamber. It's not the one that you see in the picture right now, but it's over here, and that shows a pulse train that has been captured a little while ago, but it will update as soon as we turn on the system. And the microcontroller based control unit is actually visible here. It's in a prototype board. You can see the two duplicate channels for controlling the power switches for the existing legacy thruster and PPU channels. And the system is originally based on a NetBurner Mod 5270 board with a little adapter board that takes the 50-pin connectors from the Mod 5270B module and breaks them out, and they are connected to the various optocouplers and then subsequently to relay switches, which are then used to channel the power to the devices. And the circuit diagram is attached in the experimental notes, so it might be useful to have a comparison between that. And over on our laptop, we have a control program, which is a direct connection via serial port to the microcontroller, and we can actually just operate it at any time by pressing the enter button and getting a menu. This is just a test menu. It has no relation to actually anything that we wanted to implement in the final version. But we have certain commands that we've programmed, and for some reference, these are based on certain commands that we tested when we had a PhoneSat CPU here with the Oriole back a few weeks ago. And this is version 4D of the two-channel control unit program. The initial few commands that I hope can be seen clearly on a screen have settings for pulse rate of 1 Hertz or 176 Hertz on the logical channel. And then they have just an enable or disable switch for each of the existing microcat channels, channel 1 and channel 2. And the way to activate them are pressing Z for activation with capital letter Z, little z for disabling, capital Y for enabling channel 2, and disabling channel 2 would be just done through Y. So if we have a look at this particular thruster, which is just again a prototype parts, basically a prototype V7X PPU connected to a generation 2 thruster assembly, and the thruster head is actually, I'll just point it out, it's right about here, and the thruster head can be disengaged and taken out for servicing But otherwise, it's actually built out of a little demo thruster kit that we had available. So I reverse engineered it or modified it heavily so that the switch is actually controlling the power input, and it's actually going and being controlled eventually by the relay thruster right here. So channel 1, channel 2. Channel 1 is this thruster, and channel 2 is going to be in the vacuum chamber, which we cannot see, but we'll see its operation in a few minutes. And at this point, I'm just going to start the display by the demonstration by just pressing the letter Z. All right, and you might have heard the click, and the letter Z will actually enable the channel. The relay is actually energized already, and you can hear a little bit of click sound. And what happens is that the PPU is actually operating, and you will be able to see the red light flash with each pulse. And in this particular legacy system, the PPU is actually pre-programmed and hard-coded set to F is equal to 1 Hertz. So it's 1 Hertz rate, firing rate. And you will be able to see the thruster itself operating. And for this, I'm going to actually turn the lights off. So if you bear with me for 1 second, or perhaps I can just do something. I can actually try to zoom in, and there we go. You can actually see almost inside of the thruster assembly itself a little spark of light. And what happens at this point is that if we A, turned off the lights, and B, we were able to pump out the air in this room, we would actually see this expand into a large plume with filled with UV band light emissions. But you can actually hear it and see it, and that's enough testing for now. We'll keep this running. This channel is independent of operation, and at this point we have already set up the vacuum chamber, so we're going to actually turn on the high voltage line. All right, that is now turned on, and this is the legacy PPU system. It's a legacy, so it's kind of old design, so it's in a box obviously. So at this point we're going to come back to the screen, and we're going to actually enable the Y thruster channel, if you will. So that is channel 2 is now on, and channel 2 is actually working, and we can actually hear a little bit of that click click. And by the way, the mechanism for the PPU is essentially the same, big capacitor, big coil, and insulated gate based transistor as this one. So we have the essential elements: capacitor, coil, insulated gate based transistor, different specifications, but otherwise simple in performance. And what happens is that the pulses are being fired pretty much again 1 second or so. That's what the default programming is. Now I've got the video recording, and I'm hoping that the video is picking up a regularly occurring flash of light, and that actually is a that's actually the arc discharge happening inside of the vacuum chamber. We're back, and as you can see, the pulses are still going, but at this point I'm going to switch over to the computer terminal, and I'm going to actually send a command to disable the second channel, which is the thruster inside of the vacuum chamber, and we're going to be disabling it 3, 2, 1 now. And the firing has stopped, and that's recording the last discharge as it happened. Now I'm going to show you control again. So I'm going to bring it back up again. The channel is enabled, so it's going to start again, and it should actually begin to pulse just as normal it should be. So we have demonstrated channel 2 control here, and I'm going to shift away, and we're going to keep the pulse train running. And I know it's all complicated because we're setting up an alpha test here. We haven't enclosed anything in boxes yet, and what's happening is that the pulse train is still going, so you can hear the big click sound. So I'm going to actually press the little Z button, and it's going to actually turn off. It just turned off, so you cannot hear it anymore. But meanwhile, that oscilloscope on the channel 2 is still operating. So they can all work. Now I'm going to show you potential for channel 3 operation, which we hope to be the precursor to version 8 of the PPU for PhoneSat. So this will be one of the first things we're doing. We're going to actually enable the pulse train. There we go. We've got the pulse train independently in operation from the various pulses. So I'm going to also turn on the second channel. So we've got turn on the second channel, and we're going to turn on the first channel. So that's capital Z. So all of that is working. So we've got 1 hertz there, and we've got 1 hertz there in operation. And here we have quite a large number of pulses, and that's actually on the bottom screen. You can see it's going to be 176 hertz. This is just a calculated signal that we were developing for another legacy thruster that can be adapted, because this is a programmable control unit. So this will actually do that. But in this case, if we want to match it with 1 hertz only, then we stop the pulse train, and I'm just going to do a digital command stop, which is 7. I'm going to set the pulse train to be equal to F is equal to 1 hertz, and then I'm going to re-enable it. And there, that's the 1 hertz pulse train right there. And that's going to actually be triggered. And we're going to be able to set it so that it can capture the trigger signal as it's firing, and the oscilloscope will, keep track of that. So at this point, what we have is a system where the 3 channels are actually being generated subject to variations in how we want to control them from a common control unit. And all of these will have to be streamlined and be reduced in physical size by using SMT components, and also the functions of the PPU system itself, the essential core high current functions of the of the pulse power unit or the plasma power unit will have to be integrated into this board, and then basically integrated with this type of microprocessor, and then made as a single subsystem, which would be called the control unit and a micro-cathode arc thruster system consisting of a thruster head and a pulse power unit. Thank you.